Welcome back. Let's do two examples that we have not yet done in class. We did page 8 in class, so I will skip that. And let's look at this function. Okay, but we're going to go through the same graphing steps that we saw before. And let's see how it works. First thing we want to do is consider both the factored and unfactored form. So it looks like I can factor out a 2x. And I have x plus 3, x minus 2. Okay, so let's try again with the focus. Okay, I don't know why it keeps going out of focus. There, okay. Very finicky tonight. All right, so what do we start? Where do we start? We start at the basics. What's the domain? This time I'll just indicate x is not equal to -3, x is not equal to 2. Okay? And so then what does that tell me about vertical asymptotes? Okay? Now I look at the factored form. Wait a minute, I have a common factor. So this can reduce to 2x over x plus 3 as long as x is not equal to 2. So where's our vertical asymptote? Just 1 at x equals -3. Okay? But the function is also not defined at 2. Well, if it's not an asymptote, what's going to happen? There's going to be a hole in the function. And that's because that's a common factor in numerator and denominator. So we have a hole. The x-coordinate is 2, the common factor. The y-coordinate is, how do we find it? We plug it into the simplified form, okay? Because it's that function that we're graphing, except at the point 2. So we plug in, and we get 4/5. So this graph has a hole at 2 and at 4/5 for the y-coordinate. Okay, does that make sense? Make sure you see how that's working. Okay, now let's talk about the horizontal asymptote. Horizontal asymptote, what do we look at? The numerator and denominator have same degree. Notice we're looking at unfactored form for the horizontal asymptote. And you can look actually in either version, the reduced or non, because you see we're going to get the same ratio. Y is going to be the same coefficients, 2 over 1. So we have y equals 2. Okay, vertical asymptote is x equals -3, and our hole is at 2/4. So all of these are going to be significant when we graph. All right, what do we want to know? Does it cross the horizontal asymptote? And this is useful because sometimes you're not quite sure how it goes. Knowing whether it crosses or not can help you out there. So what do I do to figure that out? I see if this equation, f of x equals 2, the y value of the horizontal asymptote, we see if that equation has a solution. Okay, so f of x equals 2. That means I'll use the unfactored form. Equals 2. Clear of fractions. And we get 2x squared minus 4x equals 2x squared plus 2x minus 12. Okay. And so, all right, then what happens? We end up with, okay, we end up with the following. That cancels. I get 6x equals I'm sorry, negative 6x equals negative 12, which means x equals 2. But x equals 2 is the hole in the function. So does it cross? The answer is no, because that's where we have the hole. Okay? So it does not cross, because where it would cross is not in the domain. X is not defined at 2. Does that make sense? So it will not cross. Okay, how about symmetry? Again, I'll let you test that there is none, because if you plug in minus x, you have, this is fine for the even powers. The odd powers are going to mess up with the 6. So you can check that out. There won't be any. Okay, oh, I forgot the symmetry. I forgot the intercepts. X-intercept. Now we can use the simplified form. Okay, so 2x over x plus 3 equals 0. That's where the numerator is equal to 0, and so x equals 0. Okay? And also we can see that if we plug in 0 for x, we get y. So the y-intercept and the x-intercept are the same. They're both the origin. Because if you plug in 0, and you can see it either from the original or from this, you can see that f of 0 is going to be 0 in both cases. I think it's my hand that's doing that, so I'll try and hold it back for you. Okay? So now we're ready to set up our number line with our function values and determine what happens. All right, so for our number line, let's see what values we're going to put on it. The domain, we have negative 3, so here's 0. Negative 3, we have a vertical asymptote. And at 2, we have the hole in the function. Okay, so again, let me see if I can get that moved back. Why is it messing up? There we go. Sorry about that. Okay, do we have anything else on our number line? Not really. Okay, because the only 0 we had was 0 itself. There was 1 0. Okay, so there's 1 0, 1 vertical asymptote, 1 hole in the function. So those are the only values we need to check. So our intervals are up to negative 3. Sorry, I don't know, I'm having trouble with the minus signs either. This interval from 0 to 2, and from 2 to infinity. So there we go. All right, so now let's find some function values. And remember, for this, it's okay to use the simplified form. It'll be easier to compute those function values. So what are some good trial points? How about negative 4? How about 1? How about, let's see, negative 1 here, 1, and 3. Okay? So if x is negative 4, f of x is 2 times the negative 4 over negative 4 plus 3. It looks like it's 8. Okay? If x is negative 1, it's 2 times negative 1 over negative 1 plus 3. It's negative 2 over 2, so it's negative 1. Okay, f of 1 is 2 times 1 over 1 plus 3, which is 1/2. And then finally, f of 3 is what? 2 times 3 over 3 plus 3, which is 6 over 6, or 1. Okay, now let's graph it. By the way, this was much easier to compute than the previous example. So this is more like the type, with only one asymptote. Not necessarily that that's what you would see on a graph, but something that's a little bit simpler to compute on the exam, so you don't have to, waste hours trying to find these function values. Okay, but let's get our picture. All right, we have our vertical asymptote at negative 3. Okay, and right, we had our horizontal asymptote at 2, and remember it does not cross. Okay, the only intercept we had was 0, 0. Okay, there was one which is both, and that in general, if the origin is the x-intercept, it will also be the y-intercept. It's so nice when it's in focus, but when it gets out, it's a pain. Okay, so now let's look at some function values. At -4, we're up here at 8. Okay, beyond the scope of our graph. All right. At -1, we're at -1. Okay. At 2, what happens? We have a hole. Remember we have the hole? And what are the coordinates of the hole? 2 and 4/5. So we want to be sure to put that hole in there nice and big so we can see it. Make sure if you're graphing this that it's visible to the person grading it. Okay, f of 1 was 1/2, which is right here. And f of 3 was 1. And I think we can kind of see the pattern just by the points that we've graphed. Okay, but now look at, again, the sign. It's positive, so up to -3 it lies above. Between -3 and 0, it is negative, so it lies below. Between 0 and 2, it is positive, so it lies above. And it stays above at the hole, okay, after that point. Okay, so let's graph it. Now remember, the asymptote thing is going to apply here. So what is going to happen in the long run? The graph is going to be coming out closer and closer to 2 for the y values, but they're getting larger and larger as x approaches -3. So they're going to look something like that. Okay? Now, in this direction they're below, but we still have the asymptote. That means they must start very close to that x value of -3. And then if we connect the dots, notice that it's below, then it jumps above, stays above. Now here's where it's really helpful to know that it doesn't cross. Remember, it doesn't cross the horizontal asymptote at all, so it must stay underneath it. And so in the end behavior, your graph is going to look something like this. And that is the graph of that function. Okay? So hopefully you're getting a good idea of how all of this kind of fits together and gives us a great picture of the function. Now with calculus we can get much better pictures, but this is pretty good. With rational functions, it turns out we can get pretty accurate pictures. Okay, I think we will stop there.